Okay, then let's look what happens for capacitors in series. So once again, we have three capacitors. This time they're connected in series. And we want to say what is the equivalent capacitor will do the same thing as those three capacitors in the circuit. The first thing we have to identify here is that each of these capacitors will have exactly the same charge, because if we think of an electron moving around in this direction and being deposited essentially on this capacitor, what that will do is it will repel an electron off this side of the opposite plate, making it positively charged. But that electron has to go somewhere, and the only place it has to go is over to here. It will have the same effect, repel one from here over to here, which will repel an electron off there, which balances up with the electron that is in this one. Okay, so there's no way I can have like a negative charge of 4 there while that plate's just +1. It will always balance out, and each of these plates always has to have the same charge on them, and it doesn't matter if one of the capacitors is bigger, one of those capacitors is smaller. Each of these will have a charge Q on the capacitors, and they will be exactly the same. Now, how much charge is stored in total then? I think it would be reasonable to say it's 3 Qs, okay, because there's 3 capacitors, each with a charge of Q. But if we kind of combine this together, there's no way I can get 3 Q of charge out of that system. So we want to use this charge at some future time to, say, power a bulb. There's no way I can get 3 Qs out of that, because if one bit of charge, say this electron, moves around like this, that just doesn't cancel out one bit of charge from the right hand plate of C3 and the left hand plate of C1. It will cancel out charge on each of those plates. That wasn't very well done, but you get the idea. So in fact, if amount of charge Q flows off C3, we'll look at it in electrons this way, that would actually remove all the charge from all those capacitors. So what we say is that each of these capacitors has a charge Q, but that in fact is the total charge, because it's all the charge we can get out. So our equivalent capacitor over here would have a total capacitance and that charge Q on it, because that's the charge that we have access to. Now, if we look at that, the other rule we have is that the voltages around a circuit have to add up to give the voltage of our supply here. So if we look at the voltage on our first capacitor, we have Q equals CV, therefore V equals Q over C. Okay, so on our first capacitor, we're going to have V equals Q over C1. That's going to be our first voltage. V2 is going to be that same Q divided by C2, and the voltage on our third capacitor is going to be Q over C3. Okay, now our rule is that around any loop of the circuit, so if we go like this, the voltage across each of the components have to add up to give the voltage of the supply. So what we know is that the voltage of the supply is equal to V1 plus V2 plus V3. Subbing in these kind of values into that equation gives us that Vs equals Q over C1 plus Q over C2 plus Q over C3. But if we look at our circuit that just has that one equivalent capacitor, our total capacitance, we can do the same thing here and say the voltage of the supply is going to be Q over CT. And if we combine these two equations together, we get Vs, Q over CT from here, is equal to Q over C1 plus Q over C2 plus Q over C3, which then gives me, if we divide by Q, 1 over CT equals 1 over C1 plus 1 over C2 plus 1 over C3. Okay, and that's the key thing to take out of this, is that if we're adding capacitors in series, we add the reciprocals of the capacitances. Now, that's the same thing we did for resistors in parallel in circuits. And you see the opposite's true for capacitors compared to resistors. So we add the reciprocals here. The key thing that people forget is you need to, at the end, once you've added the reciprocals, you have to find the reciprocal of that to get the total capacitance. So let's look at a small example. So let's say I have a circuit and I have two capacitors that are in series, and let's make them, I know, 2 microfarads and 4 microfarads. So when I want to add those capacitances, I do 1 over CT equals 1 over C1 plus 1 over C2, 1 over CT equals 1 over 2 plus 1 over 4. Now you can let your calculator do the hard work if you want, but that would be 2 plus 1 over 4, which means that CT is equal to 3 over 4. Sorry, 1 over CT equals 3 over 4. What we then need to remember is to flip both those equations really. So CT is equal to 4 over 3, which is 1.333, and we need to realize all those numbers I was dealing with were microfarads. Kind of leave that out in the equation, then just put it back in again afterwards to make our unit for the total capacitance consistent with what it was for the individual capacitances. Okay, that's quite complicated. The reason for it is quite complicated, and you may be asked that in an exam. So what I'll do is watch this video a few times, maybe try and get your head around it, read over the that section in your textbook that deals with it as well. But probably the most important thing is that you can use that equation correctly. So try the questions below from the textbook and check the answers in the back of the textbook just to make sure you're getting these right, because it's kind of the basis for all our circuits that deal with capacitors.